So what we've got here, and this is going to, we're getting to the part now where we're actually able to do what I think are some of the hardest things for this class. The hardest thing for this class is not necessarily the math. It's thinking and being able to interpret and understand what to do when. Because they're not going to flat out come out and tell you, hey, you need to do this type of test in this problem. They're just going to say, is there evidence of a difference? Is there changed? How much do you think it's changed? They're just going to say words like that. And you have to be able to tell by looking at the problem what test is appropriate. So here we have a choice. We have a choice between a paired test versus a two-sample test. What do you think? Here, two-sample? Two-sample? Why? Yeah, your clouds are going to be independent. One cloud is not going to be impacting another cloud, I don't think. By the way, this is actually a true thing that they have, or they at least used to work on. I don't know if they've given up on it or not. This idea of seeding clouds. Have you guys ever heard of that before? It's when you seed something, you're planting, right? So they're trying to figure out ways, if there's a way to plant a cloud, make it rain. Make it rain, y'all. No? Wrong thing totally. I don't know if I just have high variability or if I'm biased with my... No? That kind of sucked? Okay. Well, seeding clouds is something that folks have worked on in the past, and it's the idea of can we put something into the atmosphere to help encourage rain? And so that's what we've got. We've got 20 seeded and 26 unseeded clouds. That means they tried to manipulate 26 and then they left 26 on their own accord. And for these two groups, they are two separate groups. And what I want you to look at here is you are going to need to make sure that you're very clear as to what we're doing. And I want you to look at the notation here. This is a paired t-test. They say mu 1 minus 2. This is a two-sample test, mu 1 minus mu 2. What that means is for a paired t-test, you want to think about your order of operations. You do what's inside the parentheses first. You would subtract first and then take the average. Whereas for these groups, you would take the average, and then subtract. And that's a very important distinction because a two-sample test follows all the calculations of a two-sample. You have your standard error is different. Everything is different. A paired test is basically a one-sample test. You go right back to all those old formulas, all that old stuff. So I don't know why there is so it says, explain your choice, state your conclusion. So if we use the two-sample test, they are not paired, they're independent. P-value here, there it is, 0.0538. And what they've got here is there's some evidence, because it really comes down to what do you claim your alpha to be. And alpha is not always 0.05. It depends upon what you're studying. It depends upon your risk of that type 1 and type 2 error, which one is worse from your point of view. Which is why there's a lot of studies, they say very first thing you should do is define your alpha. Before you even do it, you have to say, this is what would convince me. And if seeding a cloud was a cheap thing, then I would say, you know what? It might not be the strongest evidence, but it might be worth trying to do it in case it is working. Like it'd be worse for me to miss out on a case where maybe I can make it rain. And imagine what would have happened if they could have made it rain over Australia during the fires. Or over a desert or someplace that's going through a drought. Imagine what good that could bring, but then you have to weigh it against the cost. And where they were with this is the cost was atrocious, ridiculously high. And if you've got really high costs, then you want that p-value to be smaller. Okay, so there might be some evidence. It's all about your alpha level. All right. So last class, what we were focusing on was trying to understand the difference between differences, between paired versus independent groups. Today, we're actually going to be doing the math for it. All right? Lots of practice today. That's the goal. So here we go. We started talking last class about assumptions and conditions For a paired test, there was one main, big, massive difference. What was it? What made this test different than the difference of means? Paired data assumption. That is the number one thing. And when you go through and you look at your data, a lot of times people are like, I don't know which test to use. The assumptions and conditions tell us what test to use. When we're talking about all of our proportions, we have to know, is it a success-failure type of a situation? Is the probability of success consistent? In order to use those, we have to have that. For means, know how many samples did it come from? Were those samples independent? Conditions tell us what test to use. And the paired data assumption is number one. You've got two groups, two samples, two numbers that you're comparing. You got to ask yourself, are those from two independent samples, two independent groups? Or is there some kind of a linkage so where you can almost write them as an ordered pair? Okay. Then we go back to the old stuff. Okay, all this is still the same. Randomization, you got to have that. Randomization helps with your variability. It helps take away the idea of bias that might be present. It helps us be able to then take our information and apply it to a larger population. Percent condition, we normally don't freak out too much on means unless we know it's a limited sample size or limited population size. The normal population assumption, what's nice about the paired data, you only have one group to look at, one data to look at. And what that's going to be is that's going to be the group containing the differences, not the befores compared to the afters. It's the difference from each of those, and you're only going to have one NPP plot, one histogram, one box and whisker plot. And ladies and gentlemen, if you can't tell by an NPP plot or a histogram or whatever it is, if you can't tell if it's linear, if it's unimodal and symmetric, try a different graph. You understand what I'm talking about? If you can't tell, try a different graph. You want NPP plots to look what? Linear. So I'm not drawing dots, I'm drawing lines. Is that linear? Is that linear? Is that linear? Is that linear? No, you've got to be able to tell, and don't just say, oh, look, I could connect these dots. They make a line. Lines are straight. It's not somebody pulling down on it and moving it to one side or the other. You've got to pay attention to that. Your NPP plot will always be continuously increasing. You're not going to see it go up and then come back down. It's always going to go up. It might go up, 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 pause, up, 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 pause, up, 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 up. It might do that, but it's always going to be increasing. That's not what you're looking at. For a box and whisker plot, here's my whole line. What would you say about that one? That's skewed. Longer, shorter, longer, shorter. You want to pay attention to those things. If you have a histogram, what do you think? That's not normal. What about that? That's, if anything, that's closest to uniform. What is uniform? Level. Unimodal and symmetric has a bump. Unimodal and symmetric is a centered, balanced box and whisker plot. Unimodal and symmetric is a linear NPP plot. Okay? So you need to look out for those things. Don't just say, hey, look, I can draw an NPP plot. I'm going to say it's normal. Oh, look, I can draw a histogram. I'm going to say it's normal. No, look at these things. Interpret them. So for the paired t-test, the mechanics for this guy, he's actually the exact same thing as the mechanics for a one-sample test. No difference. The only thing that you're doing here, please look at the null hypothesis. It says mu d is equal to whatever your number is. Because like when we're talking about, I don't stand very well apparently. That was weird. I swear I have had orange juice and that's it. Okay. So when we're doing a paired t-test, you're always looking at just one mean. And it's the mean of the differences. This is saying mu sub 0, that means just whatever your null hypothesis number is. Maybe but we believe that it doesn't matter what diet program you're on, you're going to lose 5 pounds if you're following the specific exercise program. So maybe we believe that the before and after is automatically going to be 5. For the most case, we're going to usually be dealing with 0, but it's not always the case. Okay? For example, if I want to take the average height of a kindergartner as they come into school, first day of school, average height of that kindergartner, when they leave school, or the heights of each student, we're looking for the average difference in height. We're probably not looking for a 0 in that case. Kindergartners, they grow like weeds, almost as bad as toddlers or freshmen in high school, right? So it's almost always going to be 0, but not all the time. Now for our test statistic, for this guy, we don't have a weird formula for degrees of freedom. It's just n-1, where n is the number of pairs. Because really, we're creating a one sample test from these two sets of numbers. And our standard error is the same thing as what we have for a one sample test. It's the standard error. It's just for these guys, we're looking at the differences, not each of the set numbers that we're given. Okay? And always, 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 we can only go with these things if our assumptions and conditions are met. Okay? And when we're describing our distribution with this, although we're saying normal enough, that's not saying that our distribution is a normal model. We're looking for the t-distribution, because the t-distribution accounts for more variability than the normal distribution does. All right, and when we're looking for a confidence interval, again, the same thing holds true. Confidence intervals are always observed, plus or minus, test statistic, critical value, times the standard error. It's just our observed here is D bar, because that says the average, the bar is the average, D is of the differences of what you saw. Okay? And again, standard error is just the standard deviation of the differences divided by root n. And your T star is based on your confidence level, based on your degrees of freedom, so you got to make sure I always put that. And I have been really with you guys showing that. And I don't know if it was someone in this class or the other class, I even had someone write, I was so tempted to make you scavenger hunt for it, but here's the degrees of freedom. It's like, thank you for holding it in. And it's as long as I can find it. It's got to be with that problem. Like if you put the degrees of freedom on the front page, no. The problem's on the back and the degrees of freedom is on the front. Nope, not going to do that. Okay? But if the degrees of freedom, you're doing a hypothesis test and a confidence interval, you write it for the confidence interval, you didn't write it for the hypothesis test, boom, it's all there. But you've got to show me, and you've got to show me your T star. Yeah, because it's not going to change if none of your other data is changing. We'll have to later, yeah. All right, so here is the way that you are typically going to be given information. And there is actually a typo on here. I'm going to have to look at it for a second. This is, how many of you guys have like driven down highways and you see like the little way stations on the side? It's, yeah, they always do seem to be closed. A way station, it's not like, hi, go on your way. It's W-E-I-G-H. And the purpose of that is to weigh the large trucks, because roads are built to handle a certain amount of weight. Bridges, all of those kinds of things are affected by it. And when it's for all sorts of different reasons. I mean, there are legal ramifications, there's everything that goes into it. But the thing is they want to be able to do it as quick as possible. So they have two different ways to do this. You'll see that sometimes they'll have what's pulled off on the side, and it's literally just kind of like a little side hump where they just go, they drive over it, they keep going. Sometimes they have ones where it's literally like a parking spot. You come in, you stop, they weigh you, you back out, or you keep going, but you have to physically stop. So that's what we're looking at here. We're looking at the weight in motion, which is where, as long as They go at a certain speed, they just keep driving, and they go back on the highway. Versus the static wait, which means they have to stop, wait for it to calibrate, wait for it to come up with its number, and then they go. And the thing is, which one is more accurate? Okay, are they equally accurate? Do they come up with the same numbers? Because accurate is one thing, and it's more about, do they reach the same numbers? So if we're looking here, we have wait in motion versus static wait. And this is saying the difference in motion minus static. I want you to look at this. Do you see they're actually telling me the order here? If you're talking about a difference, you must tell me what order we're going in. So I think this is correct. So this minus this is negative. Make sure that these are all right. Yeah. Oh, because that's my corrected typing. I looked like I used to have it. The textbook gave this in the wrong order. They said static minus motion, and it was the wrong signs. So you got to look at that. This is the way a lot of times you will be given data on an AP exam. They'll say, here are your lists, and sometimes they'll be really nice. They'll even say down at the bottom, mean, standard deviation, sample size for each of these. So you might not even need to use your list. But what you have to understand is, am I going to use these two, or am I just going to use this one? The one. Why? Okay, but why? Why am I using a difference rather than a one sample type calculation versus a two sample? Because I've got two things here, right? Why am I using this? It is for the same truck. And that means when you go through this, ladies and gentlemen, don't just tell me data is paired. By what? What is pairing them? Data is paired by truck. Data is paired same individual before and after. It's paired husbands and wives, couples. Okay? You've got to give me a why. Don't just say, yay! Just like data is independent. Okay, why? Two colleges should not affect each other's average GPAs. Or two cars, two manufacturers should not affect each other's average miles per gallon. You got to give me some stuff here. And so what we're looking for here is, it's simply saying, is this method, are they consistent? Do you know what it means to be consistent? Consistent mean. Same results. No difference. Okay, so what I want you guys to do is I want you to check your assumptions and conditions. We're going to do everything with this, I think. Let me see. Yeah, we're going to walk through pretty much the whole shebang here. I want to show you something here. What I've gone and done is I have put in both of these two columns. I'm not expecting you to do that. I just want to make sure that you guys understand that this is a possibility. So if they give you two columns that you decide are paired, you can then, for your third column, arrow up to where you're hovering over list 3 and simply say, I'm going to do motion minus static. So I'm going to do list 1 minus list 2. It'll calculate all of those differences for you. Okay? So if you're not given that third column, that difference column, you don't need to calculate it for every single one. Just put in your data and say, hey, make that math. Do that math. Okay? I just wanted to make sure you guys could see that that is a possibility. All right, so before I kind of go over the answer, let's just make sure that we've got the diagram, the description, the things that you need. So what do I need to see a picture of? Which one of these? 1, 2, 3, 1 and 2, 2 and 3, 1 and 3, 2 and 3. What do I need? Just 3. So I'm going to go to my stat plot, And I can change it very easily to just choose a different list. So I'm going to do list 3. Which kind of graph do you want to see? You want NPP? Let's take a look at the NPP. So I'm just going to zoom stat. Oh, I have too much other stuff turned on. So I have my plot 2 turned on. Let me turn that off. And if you see that, it's just an easy, quick fix. Let me do it again. Zoom stat. What do you think? Is that a line? No. What do you say? Not really linear. To me, if I were to describe this, I would say that almost looks like a cube root, except for over here, it's not linear though. Do you understand what I'm trying to say here? Don't automatically get into this habit of, oh, I have data, it is linear. It's not. That's why we draw this. And so if that's the case, when we're going through these problems, what you would do, you would draw out your data, take a look what it looks like. I go ahead and list all sorts of different things. Like this is what I would have gotten from doing a one sample t-test. Does everybody understand that's the command you're using in your calculator? A one sample t-test over the differences. That's why it's d bar. You can see my standard deviation. You can see my d bar, my sample size, which tells me my degrees of freedom. That is not linear. It is paired by truck, and truck weights should be independent. 2 out of 3. But I would be very, very careful about how I interpret my results because the data was not normally distributed. Sometimes that's all you can say. It's not a perfect world that we live in, but you've got to recognize the fact that there are things that can get in the way. Okay? And let's see here. If you were to do that as a histogram, this is what the textbook did, like actually adjusting their bins for integers. And if you look at that, that's not really normal. Yay, I've got a high point, but I've got gaps. I've got stuff out here. Do you understand what I'm talking about? That you should be able, if you can't see it in one, if one is causing you confusion, draw another. Do a different one. It's okay. And if you're looking at it on your graph and you're going, I can't quite tell on my calculator what I'm supposed to say for this, go back to your stat plot, turn it into something else. Whoops, it's too far. Here we go. Let's do that one. Zoom, stat. Yeah, that does not look normal to me. That's weird looking. I don't know what I would call it. Weird is probably a good descriptor. But do you see the point I'm trying to make here? Okay. So now that we've done all of this, did everybody get this data? Get what your average difference was, the standard deviation of your differences, the sample size, the degrees of freedom. And I do this, and I was so tickled pink looking at some of your guys' quizzes. I do all of the computer output just in a little bump, just like that. To me, it makes it easier. I know I have to show it someplace, so why not kick out everything the calculator gives me all at once? And I've seen some people say, okay, that means if you're doing a hypothesis test, they would say T equals p-value is. They would like literally just put out all their calculator information. Wham, bam, thank you, ma'am. Okay? Now we've got the data in your calculator. Using that data, find a 98% confidence interval. We've already done our assumptions and conditions. Do everything else. Bless you. What needs to be shown for confidence interval? All we've done are the assumptions and conditions. What would you say next? Ladies and gentlemen, if you drew an NPP plot, please write NPP of differences. If you are doing a histogram, you write a label underneath saying differences. Same thing with a box and whisker plot. You've got to be able to clearly identify what all of your junk represents. And no, I'm not going to sit there counting out the number of dots that you have, but it should be pretty darn close. Are you using a one-sample t-test or just a t-test? Are you doing a t-interval? Are you doing a two-sample t-interval? What are we doing? One sample, t-interval, or just t-int. Should you use data or stats? Data. Even if you ended up calculating the statistics that goes with it, if you have data, please use the initial data. Because if you're using statistics, unless you know that those numbers were not rounded in the least bit, that's going to throw your answer off. Okay, so you're doing a 98% confidence interval. So for you guys to catch that conversation, you want to make sure that you note what the labels are. So in this case, it says weights are in thousands of pounds. Do D bar. Because when you indicate X bar, you're saying that it's just one list of data. D bar means that you found the differences before you did that. Okay. What do you think you should have followed up your assumptions and conditions with? What should you have said? Okay. But I don't, yes, you guys are not very good mind readers, are you? Don't know exactly what I want you, what is this crazy woman thinking? Were the assumptions and conditions met? Not really. Do you understand what I'm talking about? Don't just say, hey, nope, yup, moving on with life. Start off by saying that the assumptions and conditions were almost met, nearly met, not met. If there's a problem, say there's a problem. We're doing a paired t-interval, t-distribution. We have all of our little bits and pieces that I previously identified. Look at what I've got here. I've got what D is. Did you someplace indicate how you calculated your difference? It's another reason why we use D here. Because if I was just using X or mu, that means I'm talking about one value. And X bar would be the average of those values. In this case, D is a difference. And I used the weight in motion minus the static weight. That's what I took the average of. That's what my standard deviation, that's what all that represents. And then for your formula, did you have T star to be 2.82? Do you indicate that someplace? We're good. Have either the formula or the formula with the numbers in it. And your answer. We all on the same page so far? Y'all are doing, I mean, seriously, maybe not you, but your calculators are doing really great with the actual computations. Yay. So I would say we're 98% confident based on our sample that the average difference, notice this is not the difference in the averages. Those mean two completely different things. Lots of differences floating around out there. Average difference between a truck's weight in motion and static weight lies in the interval from negative 1.295 to positive 2.7747 pounds in the thousands or thousands of pounds. Now, would I have evidence that there's a difference? Cameron? Since zero's in the interval, it's possible there's no difference. I do not have enough evidence to claim that there is no difference. Now, if I was saying negative 1.295 to 2.77 pounds, maybe with that I'd be like, dude, those are like spot on. Thousands of pounds? That's a little bit more. But I don't know what the overall scale is. And actually, if we go back and we look at the data they gave us, we're looking at an average of, I don't know, it looks like somewhere around 30,000 pounds. So yeah, it's not too big of a difference. All right, so same idea, different context. For this one, I'm giving you a histogram. You don't have to draw it. You do have to comment on it, though. And I'm giving you the statistics rather than the data. So we went and got a lot more ducks. Okay, so what this is this is a different problem dealing with, what is this, highway versus city fuel efficiency. And they had a whole bunch of cars. So this is what this is the display. After deleting an outlying value of negative 27. Do you understand what I'm talking about? Cutting that out. Why might we cut it out? You're making my picture look ugly. Bye. Why might we throw something like that out? I mean, minus city. Have you ever heard of a electric vehicle? Electric vehicles, right? Do they get the same miles per gallon, or even a hybrid? Do they get the same miles per gallon for city and highway? Electric vehicle, yes, because it's powered. You don't have any gas. A hybrid, they get horrible city miles. Yeah, okay, I'm not going to. Or do they do better highway? Highway is better, like significantly better? That's just a hybrid vehicle. Like this was done back in, I don't know, back in the day when hybrid vehicles were just coming out. So these were all. So we have to have reason to throw it out. So if I'm going to throw it out because it's a hybrid vehicle, therefore is in a different group compared to these guys, maybe I throw it out because somebody was an idiot and left a digit off of the score. Kind of like I did with half of my quizzes for pre-calculus the other day. It's like, oh yes, you got a 4 out of 30. So I have a 24 out of 30. That happens. We are humans. We make mistakes. Okay? So, run through it. Okay. Huh? Well, if you took it today, you would have been out of luck because the internet's being funky. All right, so this problem, we're actually not given a lot of that beginning data. Do you know what I'm talking about? How it was collected, a lot of the stuff that we need to use to check the assumptions and conditions, right? But I can say that this is paired because we're doing highway and city, and it's going to be paired by vehicle. Yeah, I'd be hesitant saying car because there's trucks, and some people get really fussy about that. So with the outlier removed, would my assumptions and conditions be met if I look at this graph? If I took that out, does that look fairly normal? I'd say that looks pretty good. I mean, for me, I would look at that and say, I don't know what's going on with those few trucks or cars. Yeah, a sample size of 632. That's freaking huge. That's the technical term for it. That's pretty darn good. So this is what we're looking at for this. The sampling distribution follows the T model, centered at 7.37. You get that? Degrees of freedom, 631. So far, so good? Standard deviation, the 2.52 over 632. Whenever they use standard deviation, guys, that is always the standard deviation of that one sample. So if you're trying to talk about the sampling distribution, you always will then divide by the square root of the sample size. Okay? Huge! Yes? It's 600. You know, that's a really, well, that would probably be a good, I would say, yeah, I guess so. Not very clear on this because it is, say, 316 cars, 316 trucks, it's 632 to 631. This should here have been 631. That should have been 630. Nice catch. That's not something you would have dinged you for, because that's just mean. Yes. That's why I'm confused, but it says this graph shows 316 and 316. So that's why I'm like, I would not mark you off either which way. I would look at this. If you said the sample size was 632, I would expect degrees of freedom 631. If you said sample size was 631, I would have expected 630. The nice thing is, that size of a sample, it's not really going to affect your answer too much. Okay? Because you're 100% right. You're 100% right. This says, after deleting it, the 632, but this one says with the data, so they're kind of counterbalancing what they're talking about. So based on our sample, and you want to talk about the fact that we removed an outlier, we are 95% confident the mean difference, the average of the differences in fuel efficiency for the vehicles lies in the interval from 7.17 miles per gallon to 7.57 miles per gallon. I did not specify in this one order. Why do you think I didn't specify order? Because they didn't tell me the order. I can't say it if I don't know it. Please don't just make stuff up. Okay? Okay? What we're doing here is I love the fact that we've gotten to this place now where we can really pull in just about everything we've talked about. Blocking. Remember, matched pairs is a way to block. Why is it important to do a matched pairs if my sample includes both cars and trucks? What is the purpose of blocking? What is the purpose of doing a matched pairs? Why do we go through that? Ding, 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 ding. Give a man a cookie. I don't have any cookies, so sorry. Say it loud, say it proud. Reducing variability. I don't want to be comparing some rundown hunker of a truck to my slick and shiny new car. Okay? So the whole purpose of doing that is to reduce variability. Even here it says the difference can be large, but we're not looking at comparing a truck's city miles per gallon to a car's highway. We don't want to compare that. So pairing removes that variability. Now, if we're looking at this here, this is going back to the truck problem. Side-by-side box plot. Do you think I could have come to a conclusion about whether or not there is a difference just looking at these graphs? Start with yes or no. Could you have come to a clear conclusion? Yes or no? Yes, raise your hands. No, raise your hands. The rest of the class that didn't raise their hands, like the 18 of you that just sat there staring at me. Why would you say you could not come to a conclusion here? Or why would you say you could come to a conclusion? Kind of eyeballing it, if it does look pretty similar, what are the differences? What would you say the differences between these two are? color. Smart Alec. But no, what he's doing here, what I'm trying to get you guys to say is that if I'm ever asking you to describe this, and there's two of them, what kind of words do you have to use? Good words. Big words. Give me an example of a good word to use in a comparative sentence. Median. Okay, those are numbers. How about bigger, smaller, more, less, higher, lower? Those are good words, yes. They're not big words. One's gooder than the other. No, that's not, a gooder is not a good word. It's not gooder. When you're using comparative language, guys, comparative language is using comparison words. So I would say the variability of static weight less than. I would say the median weight in motion is what compared to the static weight? Greater. I would say the maximum weight in motion is greater than the static weight. I would say the minimum weight in motion is less than. I'm trying to get you guys to use comparative language. You would not be able to tell by this. It looks very close, but it's kind of like that wishy-washy. Remember where we were at the beginning of the year talking about independence? Is it the same? Is it not the same? I don't know. That's the problem with this. When I'm just looking at all of them like this, maybe the heavy trucks, when they're doing weight in motion, are lower than they actually were. And maybe when they're static, you can feel that difference more. Maybe the weight, I don't know if you guys realize this, but even the simple act of opening or closing the windows can affect what the registered weight is when you're in motion. Speed does too. But what we're looking at here, these are the same vehicles. I don't know if the vehicle that's on this quartile pairs up with the vehicle that's on this quartile. So I cannot compare them that way. All right. You get to choose. I think I already know your answer to this, whether or not AP statistics decreases student anxiety about statistics. Yeah. Consider it this way. Someone's going to take a statistics course in college. Okay? People who have had AP statistics versus people who have not had AP statistics going into their first statistics class in college. That's what they're looking at here. Not have you learned to be afraid, to be very, very afraid. Okay, this is in your notes, by the way. What is problem number 1 asking you to do? Know what? Hypothesis test. And ladies and gentlemen, a lot of times they're just going to say, do the data and indicate, and yes, that is correct notation, do the data, indicate that anxiety levels decreases after students take AP stats. A lot of times they will not put that final sentence there. The first sentence implies the second. Okay? And if they ask you how much of a difference, that implies a confidence interval. Okay, so you're going to work through the whole entire shebang from start to finish. So working through, watching what you guys did overall, I was actually really impressed with the work that you were doing. My biggest concern that I saw out of everybody was about how you wrote your null and alternative hypotheses. Okay, so that was the number 1 issue. I didn't look too closely at your assumptions and conditions. I was focusing on the number type stuff that you were showing. When we're talking about this, D is going to be the difference in anxiety levels, and we did post minus pre. So you still want to identify that, but when it comes to your mean for your hypotheses should always be in terms of a parameter. Whether that's P for proportions or mu for means, it has to be in the terms of a parameter. then you can either use a subscript D for the difference, or it's perfectly fine. I saw some folks doing 2 minus 1 for the second group minus the third group, if that was identified, or doing post minus pre in subnotation here. That's perfectly fine, but there should only be one mu, and then this stuff should be in subnotation. It's just kind of hard to do that with lowercase letters, all of it in subnotation. And I saw a couple folks using mu sub 0 for the number, but mu sub 0, we see that in our notes because that says whatever your null hypothesis number is. That's what that's talking about. Mu sub 0 is whatever your null hypothesis number is. That is what that goes right there. Okay, so I have a histogram on mine, basically because it was one of the prettiest histograms we've seen. I mean, it was beautiful. It was gorgeous. If you used an NPP plot, you would have seen those stacked dots. And again, what do those stacked dots mean? It's the same value, multiple things through the same value. So whenever you see those stacked dots, just kind of go through the middle of that. Where would the middle of all of those be? And they do that so that you can see that it's not just one value, but there are multiple things in that location. Okay? And so we've got our paired t-test. Make sure I can find your degrees of freedom someplace. Most of you guys are doing a nice job of like putting this in ways that I can find your work. Your t-score was negative 3.92. Are we all okay on that? And the p-value ended up being 0.0007. Anytime they give you a p is equal to something to the e negative number, you're more than welcome to just say approximately 0 with that. Do you understand what I'm talking about? Please do not give me p is 7 point something, because p-values have to be between what numbers? 0 and 1. So you've got to be very alert to that. So with the p-value basically 0, that's definitely going to be less than our alpha. We reject the null. Just a comment in general, some people are going through and stating a null hypothesis. They're saying we reject the null, that there is no difference in pre and post test scores. You'll see me cross that out because it's just not needed. Really, the only one that you need to state is the alternative. We support the claim that taking AP statistics decreases students' anxiety about statistics on average is really kind of what's missing from that. Believe it or not, if you end up taking stats in college, you're going to be in a much better place. The anxiety is going to come sooner or later. Why not do it sooner when you have a support system, rather than later when you're paying for the course? Okay. So this does match, and I just kind of want to come back to this over and over again, that our hypothesis tests and our confidence intervals should come to the same conclusion if alpha and your confidence level match with whatever type of test you're doing. So it does match here. We're doing a paired t-interval again. For the t-interval, my mean changes to now to my observed difference. My t-star here was 1.75. Did you guys show that? Write that down. Okay. So based on our sample, we're 90% sure that AP Stats decreases students' anxiety levels about statistics on average between 0.62 and 1.63 points on our scale, whatever that scale is. Because that would mean something different on a 10-point scale versus a 20-point or a 5-point. Okay. Questions about that? How are you feeling with this stuff in general? We getting a little bit more comfortable with this? And I think what you're going to see is really the tough part is now going to be what test do I use when? And trying to remember all the things that we've learned about when can I say cause and effect? What do you need in order to say cause and effect? You need an experiment. What does something need to be considered an experiment? Some sort of control, random. You always need randomness, but you need some manipulation of factors. Okay, you need to understand what's the difference between stratifying and cluster. What is the difference between stratifying and cluster sampling? Yeah? All of one group is cluster. Some of every group. Right. All of some versus all of one. Sum of all versus all of one. What? Stratify means to get something from every single group. Some from all groups. Cluster means you get all of a group, whether it's some of your groups or just one of your groups, you get all of some. It's the order of those words. All right. So you have a My Math Lab, your homework, due Sunday night. You are going to have a quiz in class on Monday. Monday, all we're doing is we're going to do a practice problem or two before the quiz, then you'll take the quiz. That technically is the end of this unit. Okay? But I'm not going to do the test until Friday. So Monday, we're going to wrap up this unit. But I want to make sure I give you guys a chance to get your quizzes back to study from before you have your test. So we will be starting a new thing on Wednesday. But it is not, and you'll even see that in your outline, but it's not going to be on the test. Okay? We have one chapter and one unit left. And that's pretty cool. So just want to make sure that you guys understand that your flip books are going to be due on Friday.